In this lesson, we're looking at the stoichiometry of a combustion reaction. We see that butane is being burned in the presence of oxygen to give carbon dioxide and water, as always happens with hydrocarbons. When I balanced it alphabetically. I started off with CO2. There were 4 carbons in butane, so I balanced it with 4 carbon dioxides. There are 10 hydrogens in butane, so I have to balance it with 5 waters. Then I worry about balancing the oxygens. 4 times 2 gives 8, plus 5 oxygens gives 13 oxygens. 13 oxygens can be provided by taking 13 over 2 oxygens. Now, if I didn't put the 2, I would get twice as many oxygens as I need, so I just put that over 2, created a fraction out of it, and I get the right amount of oxygens. If having fractions doesn't appeal to you, then you can simply multiply everything by 2, and you'll have everything with whole numbers. So 2 butanes require 13 moles of O2, 8 moles of CO2, and 10 moles of water are produced. And in this calculation, we're asked how many moles of water is produced from 25.5 grams of butane. So the first step in doing all these calculations is to find out how many moles of whatever substance is being reacted will react with whatever else, or will produce whatever else. We'll always go to moles. First, we find the number of moles of butane, and that is 0.43. Then we multiply by the stoichiometry of the reaction, which is 10 to 2. 10 moles of water are produced for every 2 moles of butane that is burned. Moles of butane will cancel, and we get 2.19 moles of water being produced. Then to find out how many grams of water, we multiply by the molar mass of water, which is 18.015, and we get 39 grams of water being produced. With proper use of significant figures, we are only allowed to report the answer to 3 significant figures, so we report it as 39.5. On the next question, we are asked to balance the combustion reaction for trioxane. Trioxane is a substance used in candle wax, among others. It has the formula C30H62. It's a hydrocarbon. Again, we balance alphabetically. We're asked in the question, if there's 50 grams of trioxane, how many grams of CO2 and how many grams of water are produced? So to balance the reaction, first of all, we note that there are 30 carbons in trioxane, so it would require, let's do this from the start so we can see how it comes out. We start off with 1 mole of trioxane, then we're going to need 30 moles of carbon dioxide. And likewise, we're going to need 62 hydrogens on the left. So how are we going to get 62 hydrogens? Well, by generating 31 water molecules. And then we worry about balancing oxygens. 31 oxygens here, 30 times 2 gives you 60, 60 plus 31, 91 oxygens, so you could write 91 over 2, and you would have a balanced equation. If having fractions bothers you, multiply everything by 2, and you will get 91 oxygens. This will be 60, and this will be 62. And we have a balanced combustion equation. In the question, we're asked 50 grams of trioxane is burned, so we're going to find out how many moles of trioxane we have. 30 times the molar mass of carbon plus 62 times the mass of hydrogen gives you the molar mass of trioxane. We find out there's 0.118 moles of trioxane. The stoichiometry is 60 moles of carbon dioxide produced for every 2 moles of trioxane burned, so 60 times multiply this by 30 essentially. This number times 30, because 60 over 2 equals 30, tells us we have 3.54 moles of CO2 being produced. Then we're going to find the grams of CO2 produced by multiplying by the molar mass of carbon dioxide. 12.011 grams per mole for carbon, 2 times 15.394 for the molar mass of oxygen. Multiply this by 3.5, we'll get that there's 156 grams of carbon dioxide produced. To find out the moles of water produced, we start again from the number of moles of trioxane times the stoichiometry for the reaction, which is 62 to 2. 62 moles of water is produced for every 2 moles of trioxane burned. 31 times this number gives you 3.66, and then we multiply by the molar mass of water, which is 18.01528, to obtain 66 grams of water after significant figures is accounted for. You'll notice that most of these problems have the same format. They all go from grams to moles, then they go through the stoichiometry to moles of some other substance, and then you go back to grams. And typically, they don't have to start at grams of some reactant. It could be starting at moles of a reactant, going through the stoichiometry, and then going to grams of the product. Or they could be asking you grams of product, switching it to moles of product, go through the stoichiometry the other way, and then find out moles of the other substance, the reactant, and then turn it into grams. So the problems can be of various types, but they all have the same pattern for being solved. You always have to go to moles.